So everybody, welcome to Circuit Analysis 2. You should be here for Circuit Analysis 2. My name is Ron Singleton, and I'll be your instructor for the next 15 weeks. I recognize some of your names from other courses, from the DC course maybe. There's a couple people I don't know. This is a face-to-face course with the option of going online, which I chose to exercise that option. The reason I didn't want to meet tonight, I'm watching the COVID numbers in Hamilton County is still purple. And some of you, if you had me in other classes, you know I take care of my almost 80-year-old mom. So I'm going to just watch the numbers, and we will meet on web this week. We'll play it by ear for next week. We don't have our first actual lab where we use the equipment for like 3 weeks, so we're okay. If you had a chance to go to the course site on Blackboard, you've already seen that there's some homework. I think I have the first 3 homework assignments up on Blackboard. You see that a couple lab assignments. The very first lab assignment is actually some math work that you'll do, and you'll hand that in. I believe it's due on the 28th. Hopefully you got a chance to look at that. If you haven't, you want to make sure you look at that, print it out, and get started on it. There's a lot of work to do on that first lab, and you have about a week to do it. So we don't need to do anything with the equipment this week. We don't need to do anything with the equipment next week. Next week you'll watch a video, and then you'll define some terms. After week 2, then we come in, we start doing equipment. So I'll decide whether we're going to meet face-to-face next week, but definitely by week 3, hopefully the COVID numbers will go down. So just kind of make sure you guys watch Blackboard, look for announcements and all of that. So I want to start by going over the syllabus. I'll take any general questions over the syllabus or anything in general after that. And have a couple other comments I want to make, and then I want to get into the material for the course. Now, if you had me for other courses, this syllabus is exactly the same as when I teach the fundamentals course, circuits course, physics, and all of that. My syllabi are all the same. Course number, make sure you're in the right course. I'm sure you are. If you're registered and logged in, you have to be in the right course. The name of this course is Circuit Analysis 2. You should have taken Circuit Analysis 1 at some point. Circuit Analysis 1 is DC. This course, Circuit Analysis 2, is AC. My name is Ron Singleton. You can call me Ron, Professor Singleton, Professor Ron. I'll leave that up to you. I have some contact information listed there. Notice that there's a number you can text. It's highlighted in red, and I highlighted that in red because that's the best way to get a hold of me if you need to get a hold of me quickly. And I'm not saying I'll respond right away because that's not a cell phone. I do not own a cell phone. However, that is a number you can text. That's a Google Voice number. And I'm going to say all the time, but I'm around or online often. So there's way more chance I will see a message sent from a student from that number than I would see it through email or any other way. So the fastest way to get a hold of me is through text. And you can, of course, email me at the Cincinnati State email, which I have listed there. And I'll be honest, I don't check that email as often as I should. I just have a lot of emails to check. And the best way, if you need to get a hold of me, I would say text me. And you can email, but texting is the best way. I also list my office phone, but I think you guys are aware that none of the professors are in their offices. So quite honestly, I haven't checked my office phone in I don't know how long. So I would recommend, if you need to contact me, text. That would be my first choice. Email would be my second choice. And then the last would be call the office and leave a message on the office phone. I have listed office hours, and you can see them there on the syllabus. Oh, by the way, guys, there is I don't know if you can see my cursor moving, but in the upper left-hand corner, if you're not familiar with this Collaborate software, there's a way you can, there's in the upper left-hand corner, right up under the hamburger menu, there's some magnifying glasses. You can click on that, and you can make the document that you're viewing, you can make that bigger. So if you have a hard time looking at any document that I share with you, you can use that feature to make it larger. So I was talking about office hours. I have office hours listed on the syllabus. Now for you guys, since this is actually a face-to-face class, probably best that you guys, you'll have access to me. You'll have access to me in lab. You'll have access to me before the class. And if you notice, well, one of the office hours, or actually I guess it is, I don't have any office hours before class. But typically I'm here like maybe anywhere from an hour to 30 minutes before class. And usually I'm sitting in room 330. If you guys had me for circuits last semester, it's the same room where we had our lab. So that's where I hold my office hours. If you need to come to see me before class, best to send me a text though to let me know you want to meet before class. Since we're going to meet face to face, all my other courses are through the web. Since we're going to meet face to face, I don't think office hours will be any issue, because you can always meet right before class, during class, or even after class to resolve any issues or get any help you might need. The catalog course description is there. I'm not going to read it. You can read that yourself. And then there is a prerequisite. I think I mentioned Circuit Analysis 1. You should have taken Circuit Analysis 1 or some equivalent course to be in this course. And I highly recommend that you take Circuit Analysis 1 and at least pass that course with a C or better before entering this course. Now, if you got a D, they'll still let you in, but I wouldn't recommend taking it if you got a D in the first course. You might struggle in this course a little bit. I have the topics listed there. Pretty much, I think I cover like 95% of all topics. Sometimes I have a little trouble getting to the very last topic, which is polyphase systems. There's just so much material in this course. It's hard to get to that. I think I've been teaching here since since 2013. I've probably only gotten to that topic a handful of times. So I'm not going to promise we'll get to that, but we'll definitely get through transformers, and we'll see how the semester goes after that. The polyphase systems is not an issue unless you're power systems. That's kind of what, if you're power systems, that's kind of what you guys deal with. You deal with polyphase systems. And if you are power systems and we don't get to it, you actually go through that in great detail when you take your power systems courses. So we'll see what happens with it. I'll try my best to get to it. The text, the class text is the exact same text you use in Circuits 1. And since I'm assuming everyone took Circuits 1, then everyone should have that book already. The lab manual is, again, it's the same one that you used in Circuits 1. However, in this course, I use some of the labs out of that book, and some of the labs I have from other sources, and a couple of labs I actually wrote myself. So we won't just use that lab manual. We'll use that lab manual, and we'll have some other labs coming from other places. So make sure you have those texts available. In case you haven't had me before, I think most of you have, but in case you haven't had me before, my grading system, I grade on a 10-point scale. So 60 to 69, it's a D, 70, 79, it's a C, 80 and above to 89, B, and above 90 is an A. And then I have, if you look, the exams, quizzes, labs, and homework categories listed and their weights. So this is exactly the same weight that I used in the Circuits 1 course. And actually, I use this in all my courses. So typically in my courses, I get 4 exams: exam 1, 2, 3, and 4. Exam 3 in all my courses is usually a take-home exam. And I plan definitely exam 3 will be a take-home exam. We'll plan on the other exams being in class, but we'll see how it works out. We never know what's going to happen with this virus. If we end up shutting down again, if things take a left turn and the number goes way up, then I'm prepared to deliver the course, at least the theory part of the course. I'm prepared to deliver that through the web, and that means you'll be taking exams at home. So we'll see how that works out. But plan on having exam 1, 2, and 4 in class. Exam 4 would be the final exam. It is not cumulative. It's only over the material from the end of exam 3 up through what we cover in the course. That will be your final exam. And then In other courses, I typically drop the 2 lowest quizzes, and I've decided, and I might have done this last semester, I think I did the same thing last semester, because of COVID, instead of dropping 2 quizzes, I decided to drop 3 quizzes. And the reason for that is I had a couple people last semester that had to quarantine, and you quarantine for 14 days. And if you have to quarantine, you miss 2 quizzes. Since I don't give makeup quizzes, well, that's your 2 quizzes right there that you kind of have to drop those because you had to quarantine. So I think I wanted to be a little bit more flexible. I decided to drop the 3 lowest quizzes. Now, I know people had questions about that last semester. Did I drop your quizzes? I got some texts and emails saying that I did not drop quizzes. Blackboard is set up, once I set up my grade book, it's set up to automatically drop the 3 lowest quizzes. So what the actual quiz score or quiz grade that you see is what your quiz grade is with the lowest scores drop. So let's say, for example, on exam 1, not exam 1, on quiz 1 you get 100, and then on quiz 2 you get 100. And let's say on quiz 3 you get 100. If you look at Blackboard, even though you got 100 on each of all the 3 quizzes, your quiz average would be a 0 because Blackboard is set up to drop the 3 lowest, and at that point, those 300s are the 3 lowest scores. Now after that, let's say quiz 4 you got a 60, it will drop to 60 and then 2 more hundreds. It's set up automatically at the beginning of the semester to drop. I don't drop those by hand. I don't wait to the end of the semester to drop. It drops it automatically as soon as I enter the grade. So whatever grade you're seeing on your Blackboard is the grade that you get. That's what you actually have. I think everything else is pretty clear. You can read this yourself. Just want to mention I don't give makeup quizzes. I drop 3 quizzes instead of giving the makeups. I will not give the makeup exam unless there's some kind of medical issue or if there's some other issue like a funeral or some emergency, but you have to have documentation for whatever that reason might be. And then there's also some stuff in the syllabus. If you have any kind of special needs or anything like that, then you want to let me know. And what I'm saying is if you have disability or any kind of special needs or any of these other things apply to you, just let me know, and then I'll take the appropriate actions. So that is the syllabus. Does anybody have any questions over the syllabus or anything I talked about so far? Okay. Does anybody have any questions, general questions? I think, Michael, you had your hand up earlier. Did you have a question, a general question, Michael? No question? Okay, well, I'm not hearing Michael respond. So let me say one more thing, guys, since I mentioned responding. So if anytime we use this web system, what I want you to do is make sure your microphone is muted. If you want to ask a question, unmute your mic, ask the question, and then mute your mic back. The way this system works is whoever's talking at the time, the video cuts away from me and goes to whoever mic is open. So it can cause a problem if your mic is open. It causes a lot of background noise and issues with the video. So make sure you keep your mics muted, and you don't have to open your cameras, but hopefully we'll do more face-to-face in this video stuff, because I actually like to be face-to-face. But I don't mind if you guys open your camera from time to time so I can see who I'm dealing with. I'll leave it up to you, though. So if nobody has any questions over the syllabus, let me see if I can unshare this. And I think you guys are now looking at the whiteboard. You should see a phone number there. This is the way I take attendance. You'll come in, you'll text that number. In the text, you want to write EET 132. In the text, you want to write your first name and your last name. So I'm going to have you do that right now. Take out your phone or device, text this number, area code 513-494-6162. Go ahead and text that number. In the text, write EET 132, EET 132, and make sure you put your first name and your last name in the text. It's really important that you do that because the way Cincinnati State works is that I have to have proof that you were here at least the first 2 weeks of the semester. If not, it affects your financial aid. So if I come in here and let's say we're doing online again next week, if I forget to ask you to text me, just automatically go ahead and do that. That's the way I'll take attendance. And then when I see you guys face to face, I'll send around a paper sheet to take attendance like I usually do. So go ahead and send me the text. I'll wait just a couple more seconds for you to do that. Send that text to me, and then as I mentioned at the start, you want to make sure you go to Blackboard and either print out or open up the document that is the topic sheet. I think it's titled Intro or Introduction or something like that in the week 1 folder. So go ahead and do those 2 things. Text me and have that sheet ready. And while you're doing that, I'm going to talk about a couple things you will need for the course. Number 1, you will need a 3-ring binder. If you had me for DC, you already have a 3-ring binder because I had you buy one for DC. If you're new to a class with me, then you will definitely need that binder. I don't know if you have enough room in your binder if you had me for DC. If you got a 1-inch thick binder, you probably do have enough room. You can just keep putting documents in there. The book that we use for AC and DC, these courses here, is kind of okay. It's not as good as the one they used to use or the one that UC uses. It's just kind of okay. So I tend to supplement the book a lot with a lot of handouts. So I have topic sheets. In this class, I have a lot of handouts, topic sheets, just documents. So you want to get the 3-ring binder and the 3-hole punch. What I would do is when I post something to Blackboard, which I'm going to try to do that on Sunday evenings, you can print that out, 3-hole punch it, put it in your 3-ring binder, and then you have a nice, number 1, you have a nice supplement to the textbook, and number 2, everything will be there in order, organized, and you can use that to study from. The other thing you will need in this class is a ruler. You're going to draw circuit diagrams. Again, if you had me for DC, you probably already have a ruler or some kind of straight edge. I recommend a clear 6-inch or 12-inch ruler. Clear, it doesn't have to be a clear ruler, but the reason I recommend that is when you're drawing the circuit diagrams, if you lay the ruler on top of a line that you've drawn, you can see through the ruler to see where the lines are. So I prefer the clear ones myself, but any type of straight edge would do. So 3-ring binder, you need that. And a way to punch your paper, 3-hole punch to put in the binder. You need a ruler, 6-inch ruler or 12-inch ruler or some kind of straight edge. And of course, you got to have a scientific calculator. And then you want to make sure you have a set of coloring pens or pencils. So again, if you had me for DC, you already have all that stuff. If this is your first class with me, you need to get that stuff. Get coloring pencils. And the reason for the coloring pencils will become clear as we get into the material. You should also have from Circuits 1 a digital multimeter. Now, this class is a little different. In the DC course, if things happen where we had to close down because of COVID or whatever, you can actually do that lab at home do labs at home pretty easy if you have the analog digital trainer and a digital multimeter. Well, in this class, we use a device called an oscilloscope, and you don't have access to that. So some of you might, I don't know, you might have an oscilloscope, but most people don't have an oscilloscope sitting at home in their house anywhere. So it's a little hard if we end up having to go completely remote online. So we'll see how that works out, but you can use a meter to make AC measurements. It's just not as informative as the oscilloscope would be. So we'll see what happens with that. So you do want to have that digital multimeter. And when you come for lab, you want to bring that with you. Even though we have them here in the lab, you want to bring it. Sometimes you got to hook up more than one meter. We have one here on the desk. If you have your second meter, sometimes it makes the lab go a little bit smoother. Okay? So, anybody have any questions before I get started? I want to get into the material. and I'll take any questions, and then we'll go ahead and we'll start. All right. Just so you know, I am recording this lecture. That's one good thing about meeting online, is that I'm on camera and I record it. So if whatever we're going over tonight, or if we do the same thing next week, if you need to repeat it, you can always go. What I'll do is I'll put this up on YouTube. It's always available on Blackboard. If you're registered for the class, you will have access to the video or videos. But I also put it up on YouTube, and that way it's just easy to open it up if it's on YouTube on any device. So you'll have access to the material for tonight, and if we do web thing next week, you'll have access to that video. When we come in face-to-face, I do not record those. I tried to do that the semester before last, and it's just too much moving the camera around. So anytime we're face-to-face, I don't record those lectures. However, I think I do have most of these AC lectures already pre-recorded from another semester. So I really don't recommend missing any of this stuff, because I won't say it's really involved stuff. It's kind of involved. So if you miss something, it's kind of like you missed a piece of a puzzle. Things could get a little difficult for you. But if something happens and you do miss, people get sick, things happen, let me know, and I'll try to refer you to a video. I think I have most of the videos recorded. Hopefully the one that you missed, I do have that recorded. So just let me know. So I want to go ahead and get into the material. I want to start. Let me start by saying that of all the courses I teach, and I teach a lot of different courses at different places, or I've taught a lot of different courses, I will say this is one of my favorites. And it's one of my favorites because it kind of brings together a lot of stuff. It brings together physics with DC and math, mainly trigonometry, and it brings that all together to understand this phenomenon of what we call alternating current. So it's one of my favorite courses to teach, and I want to kind of go back to what you learned in DC. And I don't want to go over what you learned in DC, but I want to talk about the concept of DC itself. Who can tell me, what is DC? What does the D and the C stand for? Explain to me what that is. What is DC? What does that mean, DC? And you guys can open up your mic and please participate. So what is DC? Abdul, go ahead.
DC stands for direct current, which is only go one way.
Exactly. So Abdul said DC stands for direct current, which means the current only flows in one direction. So with DC, current flows in one direction, and it stays at one level, one magnitude. So what I'm saying is, where do you get DC? Well, where you get DC most of the time is from a battery. Let's say a car battery, for an example. Your car battery is a 12-volt device. It puts out 12 volts. And so that 12 volts, if you hook up a circuit to the terminals of the battery, the current will flow one direction, and that current will have a certain magnitude. It won't change. The voltage won't change. It stays at 12, and the current level won't change as long as you don't change the resistance hooked up to the battery. So DC stands for direct current, but what about AC? Does anybody know what the A and the C stands for when I say AC? What does that mean, AC? What is it?
There'll be alternating current.
It will be alternating current. Alternating current. So what does it mean to alternate? And I'm going to go into the details of that. Now, we're going to get really heavy into that, and a lot of people just skip over that part of it. But I want to get into that because that's going to help us understand how a lot of other kind of components that we use in this course, how they understand how they work, how they operate. DC stands for direct current. AC stands for alternating current because the current starts off at 0, builds up to some maximum value, and then goes back to 0. And while it's doing that, it flows in one direction, and then it reverses and goes in the other direction. So let me show you what I mean on the board. You know that we get DC from a battery. DC comes from a battery. AC comes from, well, for now, I'm going to show you different places we can get AC. But what you're familiar with, it comes from like the wall outlet, which is really hooked up to a generator. We call that a rotating machine. So if you, let's say you got a lamp, and you know the lamp has, here's a lamp, I'll make a lamp. And the lamp has a cord on it, and that cord plugs into the wall, and it has those 2 blades on it. Sometimes it has 3 if there's the ground on it, but we won't worry about that. It has the 2 blades on it, and you plug that into the wall. What AC does, one of the things AC does is it does this. AC will start off flowing in one direction. It goes up through the lamp like that, and then the current will reverse and flow in the other direction. Go up through the lamp and go back the other way. And so that's the alternating part. It goes one way and then it goes the other. They call that an alternating current. It goes back and forth, it alternates. In addition to alternating, it also starts out at a magnitude of 0, a value of 0, and then it goes up to some maximum value and goes back down to 0 while it's doing that, while it's alternating. Now, guys, if you have a question, go ahead and what I need you to do is, if you got a question, open up your mic. You can interrupt me. Don't feel bad about that. Open up your mic, ask your question, and then close your mic back. If you see me look off the camera over here, my computer is over there. And when you guys send me a message, I know you can text me or you can message me or whatever you call it, and it pops up, but I can't read it from here. I got to step off to read it. So if you got a question, go ahead and ask your question, and I can answer. Just interrupt me, and I don't mind that at all. So anybody have any questions? Somebody is Abdul. Abdul, I think you sent a message out. Do you have a question?
No, I got no question.
Okay.
I have a question.
Okay.
If the current is alternating and it goes back down to 0 on a phase, then why does your lamp not turn off every phase? Or why doesn't?
Who's asking me the question?
Oh, my name is Jacob, sir.
Okay, Jacob. Well, you know, Jacob, I really like that question. You guys, let me tell you what I like about his question. I like it because he's thinking. I can by the nature of his question, I can tell he's really thinking about what I'm saying, and I like that. So here's his question. He's saying that if the current starts off at 0, if it's 0, then that light bulb is off. It takes a current to light the light bulb up. Here's what should happen. It starts off at 0, so the light bulb is off. Then the current starts to build up, and as it builds up, the light bulb should get brighter, and then it drops back off to 0, so the light bulb should dim again, and then when the current reverses, the same thing should happen over and over again. So what Jacob is saying is, why is it not that right now I'm looking up at the lights at the ceiling, how come they're not off or blinking off and on? And the answer is they actually are. They actually are. Anytime you use alternating current, now there's some exceptions to this because there's some situations where what I'm going to say is not true. But strictly speaking, I'm looking up at these are fluorescent bulbs, by the way, guys, in this room. They're fluorescent. The long tubular bulbs are fluorescent. You know a fluorescent bulb, incandescent, and the LED bulbs. You're aware of those. Well, right now, if you're in the room, look up at the light. If you have a light or a lamp in your room, that light is actually blinking off and on. And so Jacob's question is a fair one. And I know he's thinking, because what he's thinking is, well, hold on a second. If there's no current, there should be no light. And so it's actually blinking off and on. The reason you can't tell that is it's doing it so fast you can't see it. It turns out that anytime something is flashing more than 12 times a second, now listen to what I'm saying. Anytime something's flashing more than 12 times per second, your eye can't tell. It looks like a smooth, continuous movement. I don't know if you guys do this, and I don't even know if you know what I'm talking about. But when I was in school, we used to make these flip books. You know what a flip book is? We used to make a cartoon. We take like a notebook, and you can draw a figure on the page, of the notebook, and then you can turn the page and draw the figure again, but move it over a little bit, and then turn that page and draw the figure again and move it over a little bit. You can, and then you can flip through it, and it looks like the figure's moving if you flip it fast enough. If you flip it real slow, there's movement, but it's like a real jagged movement. If you're in the video, I don't know if I have any people that make videos, there's something called, there's a term they use in videos, FPS. Any video people out there know what does this mean, FPS? What's that stand for? And I got
frames per second.
frames per second. That stands for frames per second. So if you record video, if you have the right camera, you have control over the number of frames per second. The more frames per second you use, the smoother the motion when you play it back, right? So it turns out that it really doesn't have to be much smoother than 12 times per second. If it's 12 times per second, it looks continuous. Now I'm saying that, Jacob, because the lights are actually blinking off and on, but they're doing it so fast, they're blinking off and on. And I'll come back to that because I want you to tell me how fast they're blinking. I'll come back to that when we talk about frequency. But the answer to that is they actually are going off and coming back on. It's just happening so fast you can't see it. Your eyes can't detect it. That's a very good question. Any more questions? Okay, well, I got a question for you. We talked about, and you understand what DC is. DC is direct current. You don't really understand AC yet. You will, but you don't understand it yet, but you know AC exists, and we kind of talked in general how it behaves. That's alternating current, AC. My question is, why do we need both? Why do we need both DC and AC? Does anybody know, why do we have both? Why do we need both? Okay, well, I'm going to assume by, go ahead.
I'll say we need both because some applications work best with AC and some work better with DC. Okay, and guys, and we'll do more of this when we're face to face. I know you guys will participate, but don't worry about a wrong answer. I mean, a wrong answer is better than no answers, okay? Just guess if you want to. I don't care. I want participation. So it was said that some applications are better for AC than DC, and that's true. That's a true statement. But I want to go a little bit deeper than that. Now, if you had me for DC, I taught the course from a physics perspective, from first principles. If you had somebody else, you probably wasn't taught from a physics point of view. So just got to kind of follow along with what I'm saying. If you had me for DC, though, remember when we talked about the resistance of wire? Let me put the formula on the board. You'll remember when we did experiment number 3. Experiment number 3 was when you had all those resistors you had to measure. I gave you like 10 resistors. You had to color code them. You had to measure them to see if they were in tolerance when you took circuits 1. And then we dealt with something called the potentiometer. And when I explained that potentiometer, I drew a long wire on the board. And we talked about the resistance of wire. I'm going to go back to that lecture. I want to show you the formula I introduced to you when we talked about resistance of wire. Here's the formula for the resistance of wire. Now, if you have me for DC, this should look familiar. If you have somebody else for DC, it's okay. We're not going to use this. It's just going to help us to understand why we need both DC and AC. So let's define these symbols. This is the resistance of wire. Resistance of wire. Can anybody remember what that is? What's the L stand for? If you had me for DC or maybe another professor, what does the L stand for? Don't have me look on here and see who had me for DC. You better know it. DC. Daniel, you had me for DC. You should know. I don't recognize. Oh, Michael, you should know. You had me for DC. What do you just guess? What do you think the L stands for? If I have a piece of wire, what do you think the L? Huh?
Stands for area.
The L.
Air.
The L stands for length. The A stands for area.
Yes.
All right. And then this one is kind of hard to talk about. I'll just get, this is the resistivity. And just in case you didn't have me for DC or your other professor didn't talk about this, let me just briefly explain what we talked about in that lab. What we said was that if we had a piece of wire, say I have a piece of wire, this L stands for the length of wire you have. That's L. How long is the wire? The A is the cross-sectional area of the wire. So if this is the wire, so this is the wire, this marker is the wire, here's the wire, and here's your eyeball. You're looking at the edge of the wire. Here's your eye. You're looking at that. If I take the wire and turn it towards the camera, then the tip of the wire you're looking at, it looks like a circle. It looks like this. So the area of that is what we mean by A. How thick is the wire? Now they talk about wire gauge, and we talked about the gauge of wire, but when you use this formula, they use another unit. They don't use gauge. So this is the cross-sectional area of the wire, how thick it is. And then this right here, this is called the resistivity, and what that is a characteristic of the material. It has to do with the makeup, the atomic makeup of the wire. And it's constant for whatever material we're talking about. So what I mean by that is, let's say you got a piece of wire made out of copper. You can look up in a material science book or maybe a physics book. You can look the resistivity up for copper and you'll get a number. And you can put that number in this equation. If you look up a different conductor like aluminum, the resistivity value for aluminum will be different from copper, but constant for all aluminum. So what this does is take into account what the wire is made out of. Now, if you're one of my students, you know when we have an equation, what's really important with equations is not so much the answer you get from the equation, it's the relationship between the variables. Can anybody tell me how is the resistance of the wire and the length of the wire, how are they related? How are they related? And I hope you know what I mean by that when I ask that question. What's the relationship between the two?
The longer the wire is, the more resistance will be put on it because there's more area of wire.
Okay, I love that. The longer the wire, the more resistance. Now the math way of saying that, the mathematical way of saying that is because the resistance of wire, R sub W, and the length of wire, L, because the R and the L are both in the numerator, then what I can write is this. I can write R sub W, and I can write this sign, and I can write L. So look at this. Has anybody ever seen this sign before in math? What does that mean? In math, what does that mean? It's not an equal sign. It's like it's alpha, the Greek letter alpha. Can anybody tell me what this means?
Is there infinity?
It's not infinity. Infinity is this. I'm drawing this.
Oh.
So this is the sign of what? It begins with a P, as in Paul.
Proportional.
That means they're proportional. This is the sign of proportionality. And so what we're saying is, when I do this, if I read it, here's what I would say. R is directly proportional to L. And I believe that was Jacob that said, the longer the wire, the more resistance. The math way of saying that is, since R is directly proportional to L, if I increase the length, if they're directly proportional, if I increase the length, then that's going to go up. If I decrease the length, the resistance will go down. If I double the length, the resistance will double. If I take 1/2 of the length, then the resistance is cut in half. Whatever I do to the length of wire, to L, then R is going to respond in the same way. That's what it means physically when I say mathematically that R is directly proportional to L. So Jacob is right. The longer the wire, the more resistance. Now, you know me, though, if you had me in classes, I don't want you to just look at the math. It's easy to shake your head and say, yeah, I understand that, but does it make sense? Does it make sense that if I have a longer wire, then that voltage has to push through more stuff? And you should be nodding your head, yes, that makes sense, that if I have a longer wire, that current has to go through more stuff, therefore it's going to be more resistance. What about the R and the A? How are they related? I got the R in the numerator and the A in the denominator. How would I write that mathematically? What would I write? How would I write it?
Means they're inversely proportional.
They're inversely proportional. So I would write it like this. I would say that R sub W is proportional to, not A, it's proportional to 1 over A. So if I have 1 in the numerator and 1 quantity in the denominator, then the relationship is they're inversely or indirectly proportional. And what does that mean? Well, that means whatever I do to this one, the opposite happens to this one. So if I take the wire and I make it fatter, that is, I increase the area, I make this bigger, then the resistance is going to go down. If I make this smaller, then the resistance is going to go up. If I double the area, then I cut the resistance in half. If I cut the area in half, then I double the resistance. Whatever I do to A, the opposite happens to R. Now, let me tell you, why is this important? Well, think about this. Actually, let me tell you a story. Let me tell you a little story. What was the guy's name that invented the light bulb? What's that dude's name?
Thomas Edison.
Thomas Edison. Thomas Edison had the whole country wired, the country back then, wired up with a DC system. He actually had electrical power in the late 1800s or early 1900s, and it was a DC system. So what Thomas Edison had was this. He had a station that produced DC, and maybe the town is over here, the houses that he had the power. And what he had to do was run a long wire from here over to here. He had a really long wire. Well, according to this relationship, if I have a really long wire, then I'm going to have a lot of resistance in that wire. Matter of fact, the further the city is from the generating plant, the more resistance I got to push through to get the current from the generating plant over to the town, to the houses. It's a lot of resistance, and that ain't good. Why is that not good? Because we'll go back to what you learned in DC. Remember power, right? I can calculate power, and one way to do it is to take the current squared times the resistance. Well, the resistance I'm talking about is the resistance of the wire. So this is R sub W. It's R sub W. Now, can anybody tell me, if I'm generating power, I want the power to come over here, right? So my meter will not be over here. It would be silly to have the meter here. The meter in your house, the electric meter, is over here on the outside of your house or in your basement. What that means is that whoever's creating the power or energy, if the meter's over here and not over here, that means they can't charge you for any power or energy in the wire. So if we look at this, if I take the current going through the wire to the house, squared times the resistance of the wire, then that's going to give me the power dissipated in the wire. The problem is I don't want the power to dissipate in the wire. I want the power to go into the house over here. So this is actually a power loss. Any power being dissipated in the wire before it gets into your house, it's a power loss. And the generating company the power company has to eat that up. They can't charge you for that. So I gotta find a way, if I want to make money, if I'm producing energy, electrical energy, I gotta find a way to reduce the loss. Well, this will help. This right here will help. R sub W is directly proportional to 1 over A. So one way to reduce the power is this wire. I can get thicker wire. If I make the area bigger, then the resistance will go down. If the resistance of the wire goes down, then the power loss in the wire goes down. But what's the problem with making the wire bigger, fatter? What's the problem with making bigger wire? What do you think the problem is? Does that solve our problem?
Well, the wire would cost more money.
The wire will cost more money. I need bigger towers, supporting structures to support the wire. Everything goes up by order of magnitude. So this doesn't really solve our problem. Now, has anybody ever heard of Nikola Tesla? Anybody ever heard of a dude named Tesla? You should have, because number one, I got a video on Blackboard. If you looked at the video, you probably already seen the name. There's a car company named after Tesla, and there's a lot of inventions that Tesla made that you use right now, and you probably don't realize that they were from Tesla. Can anybody tell me about Nikola Tesla? Who was he? Who was he?
Tesla was an engineer who created alternating current. Also created the electric motor and many other things like radio signals and other stuff.
Beautiful, beautiful. So if you don't know who Tesla is, you will, because if you look on Blackboard, that's one of your first assignments. I think it's due on the 28th. There's a video you got to watch on Nikola Tesla. Tesla is called the father of AC. Tesla was a genius. Tesla was the man. Somebody asked Albert Einstein, they said, Professor Einstein, Dr. Einstein, how does it feel to be a genius? And he replied, I don't know, ask Nikola Tesla. Even Einstein himself paid homage to Tesla because Tesla was the man. He was just brilliant like that. And so there's a lot of patents in his name. But the main thing is that Tesla was the father of AC. Tesla actually worked for Edison. Tesla also worked for Westinghouse. When you look at the video, you'll go into some of the history. But here's what Tesla did that was really, really kind of, the only word I can think of is slick. Tesla understood that if he, instead of delivering the power in the form of DC, if he delivered it in the form of AC, then it's much more efficient to do that. Now, I got to explain to you how. Don't let me get away with this, not explaining how. But this is the reason why we have two. And I'm going to explain it in just a second. This is the reason why we need both AC and DC. It turns out that it's much more efficient to transfer power in the form of AC than it is in the form of DC because of this power loss effect. This is called Joule heating. Joule heating. The power loss that happens in the wire when you run current through it, and the resistance of the wire dissipates the power loss, it's called Joule heating, and that's a bad thing. So let me tell you what Tesla figured out, and I don't know how he figured it out. You're not going to really understand the complete story because there's a device we got to talk about to really understand it, but you'll understand it enough to see why this guy was so smart, or considered to be so smart. There's a device called a transformer. This is what we have to talk about. Now, unfortunately, we don't get the transformers until like week 10 in here. But I'm going to tell you in short what a transformer does. A transformer does this. A transformer. I'll draw it as a box. We'll actually put together, design on the board a transformer. You'll know exactly how it works. But that's week 10. So right now I'm going to draw it as just a box. So here's my transformer. And a transformer has a place to put in voltage and a place to get out voltage. So my signal goes in here and get my signal out here. Now, transformers are kind of special because with a transformer, now I'm going to assume that we have a perfect transformer, an ideal transformer. With a transformer, and this is what Tesla figured out. This is what he figured out. With a transformer, the power that you put into the transformer and the power you get out of the transformer got to equal each other. Nothing special about that. And really, from physics, that's just the conservation of energy principle, said another way. But power into the transformer, it's got to equal power out of the transformer. If you remember from DC, if I want to calculate power equals V times I. So if I want to calculate the power going in, what I take is the voltage going into the transformer, and I multiply that by the current going into the transformer. If I want to calculate the power going out, then I take the voltage coming out of the transformer, and multiply that by the current coming out of the transformer. And what Tesla figured out is that these two powers got to be equal. So here's something special you can do with a transformer. Power in and power out got to be equal, but the V and I can be in any combination I want. So with a transformer, what a transformer allows me to do is to take a voltage and make it real big or make it real small. Now remember what I said. With a transformer, the power in and the power out has to equal each other. Let's say I have a transformer that's I don't know. Let's say I have a transformer that's 6 volts, and the current into the transformer is 2 amps. How much power do I have going into the transformer if the voltage going into the transformer is 6 volts and the current is 2 amps? What's my input power? What's my input power? Using this equation, what would be the input power?
12 watts.
12 watts. So on this side of this equation, going into my transformer, I got 12 watts. So I'm going to erase this right here. I got 12 watts. Now what the transformer allows me to do, it allows me to make the voltage as big as I want or as small as I want, with the condition that I cannot change this power right here, because P in and P out got to equal each other. So if I have 6 volts going in and 2 amps going in, the transformer can make this voltage bigger. It's called a step up. If I make the voltage bigger, the transformer is called a step up transformer. So I can step the voltage up. Let's say I step the voltage up to 12 volts. If I step the voltage up to 12 volts, but for the transformer, P in and P out has got to equal each other. The only way for this and this to equal each other is if I make the voltage bigger, what has to happen to the current?
The current has to get smaller. In
Gotta
this
get
case,
smaller.
1 amp.
In this case, 1 amp. Because this side's got to equal 12, and this side's got to equal 12. So Tesla figured this out. With a step-up transformer, I can make the voltage bigger, but in exchange for doing that, the current gets smaller. Now, how does that help us? We'll go back to this equation. I erased it. Go back to this equation. Since I figured out that from this wire equation that P loss equals I squared times R sub W, what I can do is I can step the voltage up, which drops the current. And if I drop the current, guess what's going to happen to the power loss? It's going to drop. The problem is you can only step up AC. This is what Tesla figured out. You can't use a transformer to step up DC. Tesla figured out you can only step up AC. And so this is the genius of the system. Now I'm going to share a document with you. Look at your computer screen real quick. And I want to share something with you. And I actually made a video of this. So you might already look at the video, but I want to talk about that just in case. Because this explains exactly what I've been talking about. So this is a power distribution system. And let's talk about the parts of the power distribution system. So right up in the upper left-hand corner, like right here, you have a hydroelectric generator. I have water. I have water behind the dam, and that water is real high. And when that water falls over the dam, it can turn the generator, which produces electricity. And that's exactly what happens here. Hydroelectric electricity, they dam up a river or a creek or a stream, and that falling water turns the blades of a generator. They call it here a turbine. The turbine turns the generator, which produces electricity. And if you look coming out of the generator, and we'll talk about generators here in a second, that generator puts out 22,000 volts of AC. That's a lot of voltage. But look at what they do with that voltage. They run it over here. Now look at this right here. Look at that. They run it over here to some what? Step-up transformers. They step the voltage up from 22,000 volts, 22 kilovolts to what? half a megavolt, 500,000 volts. Why do they do that? Because they realize if we step the current up, we step the voltage up, the current will drop. The current drops, that means the power loss in the wire will decrease and decrease greatly. So that's the purpose of the step-up transformer. So what happens is that the water falls over the dam, it turns the turbines, which turns the generator, which produces electricity, voltage in the form of 22,000 volts, and then we run into these step-up transformers. The voltage is stepped up, and then we send that current and voltage out over these power lines. Now, these power lines, they're not telephone poles like you see on Reading Road, or if you look out your window on the street. These are not those. These are the things that you see when you're on the highway and you're in the middle of nothing but cornfields and cows. You're out in the middle of nowhere and you look over and you see those big metal towers. That's what this is. This is part of we call the national grid. This is how we distribute electricity, electrical current in the United States. And so we deliver it across these transmission lines at 500,000 volts. And then we come over here. Here's an industrial customer. Now notice what happens here. They step the voltage down. These are step-up transformer. Right in here, we have step-down transformer. So now I'm going to bring my voltage back down. If my voltage drops down, my current goes back up. So my current is increased. Maybe this industrial customer can use that higher level of current. But notice the voltage is decreased from 500,000 volts down to 66,000 volts. And then it steps down again right here to 4,800 volts. And then now we're getting into residential where you live. We go from 4,800 volts, 4.8 kilovolts, down to 240 volts. And they split that 240 volts so you can have 220 in your house if you have like a washer or dryer you need to run. Or you can have 120 in your house if you want to run a TV or a lamp or something like that. But the whole system is based on these step up and step down devices called transformers. Tesla figured all this out. So that's pretty cool. If you think about it, it's ingenious. So my question was this: what is DC and what is AC? Well, we figured that out. Direct current, alternating current. My next question was, okay, well, why do we need both? Why do we need both DC and AC? And somebody said, well, some applications work better with DC and some work, and that's right, some work better with AC. But the truth of the matter is, the most efficient way to transfer power from one place to another is in the form of AC power, not DC power, in the form of AC. Okay, Singleton, well, all right, that makes sense. But, well, if that's the case, why not get rid of all the DC devices and have everything AC? Let's just make everything work off of AC. Why don't we do that? Get rid of DC. Well, that won't work either, because it turns out like any DC device, anything that works off a battery, like your cell phone or a flashlight, those are simple devices. We can design the same device to work off of AC, but the electronics to make that device work will be way more complex. It's most of the time, it's way more simpler to design a device to operate off DC than AC. So here's what we do. There's a trade-off. What we do is to power devices, we use AC. Not to power devices. When I want to transmit energy, electrical energy, I'm going to transmit it in the form of AC. When I get the electricity where I want it, then I'm going to take that and change it from AC to DC. Now, that's not true in all cases, because some devices like a washing machine or an oven, something like that, or you might have an AC motor, those run off of straight AC. But most devices run off of DC. Most devices run off of DC. Well, hold on a second, Singleton. I don't believe that, because like my TV plugs into the wall, my computer plugs into the wall. When I look around this room, there's so many things plugged into the wall, they're all AC. To which I reply, no, they're not. They're DC. Inside of your TV, for example, yes, your TV plugs into the wall, but the actual electricity inside your television is DC. there is a circuit or circuitry inside your DC to convert the AC to DC. It's the same thing your phone does. So you walk around with your phone, you got a DC battery in there. That battery powers your phone. But what happens when the battery goes dead? You plug your phone into a charger, and that charger takes the AC from the wall outlet and changes it to DC to charge your battery. With a circuitry that does that is exactly what's in your television set, exactly what's in most devices that you think is AC, but really it's a DC device. So the takeaway is this. I use AC electricity or AC power when I want to transmit the energy. Once I get the energy where I need it to be, once I get it to where it needs to be, I take that energy and I change it from AC to DC because the design of a DC device, all things being equal, the design of a DC device usually is way simpler than the design of an AC device. So in short, guys, we need both. We need both AC and DC. So you spent 15 weeks last semester or whenever you took DC, you spent 15 weeks going over DC stuff. Here's what we're going to do in this class. The same thing you did in the last class, DC. We started off talking about Ohm's law, right? Ohm's law. And you talked about power, Watt's law. And then you talked about series circuits. And then you talked about parallel circuits. And then you put the two together, you talked about series parallel circuits. And then you said, all right, well, what if I have a complex circuit, the series parallel circuit, with more than one voltage source? How do I do an analysis on that? I can't use Ohm's law. It's too complicated. And so we showed you how to solve multi-source networks using what? Mesh analysis, nodal analysis, superposition, Thevenin's theorem. We looked at we're going to do exactly the same thing in this class, but now instead of the power source being DC, the power source is going to be AC, which means that since the AC signal is way more complicated than a DC signal, the analysis for the circuit or the problem that you're going to do is going to be way more involved. AC is way more complicated than DC. And so we can't just use simple arithmetic to solve an AC problem. We have to use some more high-powered math. So in this class, of course, there's a lot of algebra, but there's a lot of trigonometry. So a lot of trig in this class. So you got to be kind of brush up on your trig. And if it's been a while, guys, I was a math teacher when I taught high school. I like to, when I deal with a concept, I'll go back, I'll review the math, and then I'll present the math in an application problem. Okay? So I spent a lot of time talking about the difference between AC and DC and why we need both. And so let me pause for a second to see if anybody has any questions. And I need to get into some material. I'm kind of getting tired. I think I talked myself to death here. So anybody have any questions over anything we talked about so far? Okay. Well, I want to take a break. So I'm going to take a little break, but I want you guys to do something. I'm going to take a break for about, I don't know, maybe 10 minutes or so, but I want you to do something. I'm going to email you a link, and it's a video, and I want you to watch this video. The video, now if you have me for DC, you've already seen the video, and I showed you that video, and I said, if you have me for AC, this video, this is what we're going to start the AC class with. So you already seen it, but I want you to re-watch it. Watch it again. I'm going to send you this video while I'm taking a break or while we're taking a break, and I want you to watch it. Now, the video is just a couple minutes long. In the video, you'll see a guy do a demonstration, and he'll demonstrate. He'll do a demonstration, and then he'll switch over to a piece of paper, and he'll start to explain it mathematically. When he does that, you can turn the video off. You don't have to watch the math. I just want you to see what he does. So watch what he does, and then when he gets to the point to where the camera switches over to the paper, and he starts to write the equations, you can stop the video. Okay, so I'm going to send the link out, and you watch the video, and you can take a little break after that, and then we'll come back and we'll start up class again in just a few seconds. But go ahead, I'll send the link out. I'll let you know when it's posted. I want you to watch the video, and we'll watch the video. That way, when we come back from break, we can talk about it, all right? So I'm going to send you the link right now, and I'll let you know when it's posted. AC and DC. We talked about why we need both DC and AC. What I want to talk about now is different ways to create AC. We know how to create DC. DC comes from a battery, or maybe I have a circuit that converts the AC to DC, but for the most part, DC comes from a battery. How or where do I get AC? How do I get AC? And the video I'm sharing with you shows a couple different ways to get AC. Label A through E, I want to talk about each of these, and I'm going to focus on one of these. So in A is basically what I showed you in that power distribution system. There was a hydroelectric generating station. Water fell over a dam, turned turbines, and the turbines spun a generator. And so what you see here is exactly that. It's a generator in A. This is a generator. And notice a couple things here. Notice number one, in each of these, they have this little wave right here that represents AC. And you'll find that there's different types of AC, but the kind of AC we're talking about is called sinusoidal AC, because if I look at a picture of what that current looks like or what the voltage looks like a sine wave, and that's what they show in each of these diagrams. And we'll look at why that's the case. Why is it the sine wave? But the point I want to make is they're showing you that if you spin the shaft of the generator, it produces this waveform, the AC current or voltage. So this is a generator, same type of generator. You hear this showing in the industrial system here. Same kind of generator that we look when we look at the power distribution system. As opposed to this one in B, that also is a generator. It's a small generator. You might have this if you have a motor home, or maybe you have a system maybe like a hospital that if they go off the grid, they still got to have power to take care of the patients. So they might have a small generator like this. This actually looks like a portable generator. You put gasoline in here, and the gasoline motor turns the shaft of the generator, turns this shaft right here, and produces AC. And then they have this, what is this? This is it's like a windmill, right? So here's a generator in the back of this, and then this thing that's showing you the wind spins. Again, I got to turn the shaft of the generator. There's a generator in the back of this, and then I turn that, and this will put out a sine wave, AC sine wave. And this is what we call clean energy, right? Because over here in A, in order to turn that generator, they show these chimneys, these smokestacks here. I got to turn that generator some kind of way. And usually we burn coal, and the coal heats water, and the water produces steam, and the steam shoots up and turns the generator. Or maybe I do what I did before, and I make a dam. The water falls over the dam, it falls down through the turbines, it spins the turbine. Some kind of way I got to turn this. Well, here the wind turns it. So this is electricity generated from wind energy, and then you call that clean energy. But look over here. D. This is a solar panel. Einstein discovered something called the photoelectric effect. You can read about that. Photoelectric effect. Basically, certain materials, when you irradiate them with light, like sunlight, it knocks electrons off, and we can use that electron to make electrical current. That's how a photocell works. And so we collect energy from the sun, but that energy from the sun is produced in the form of DC, not AC. So we got to run it through this thing right here. This box right here is called an inverter. An inverter takes DC and changes it to AC. An inverter takes DC and changes it to AC. It's done electronically though. And in the last case, this is called a function generator. We have this in our lab. This is your AC power supply right here. So again, it produces an output of AC waveform, but it's done electronically. So D and F produces AC waveforms electronically, but A, B, and C how are they related? What does figure A, B, and C, what do they all have in common?
Rotation?
Rotation. All of those machines have to rotate to produce electrical current. Now, earlier in the lecture, I referred to something called a rotating machine. A rotating machine. And this is what I mean by a rotating machine. A generator, and both A, B, or I should say all A, B, and C, these figures are rotating machines. And I want to show you that if you produce electricity using a rotating machine, the kind of electricity you get is AC. Not just that, though, it's got to be a sine wave. I'm going to show you there's actually different forms of AC. There's 3 different ways I can get AC. But on one of those ways, when that AC is produced by a rotating machine, then it has to give you a sine wave of AC and not anything else. So we'll talk about that. All right, so these are some different ways that I can get AC. Now, I asked you guys to watch a video while we took a break, and hopefully you had a chance to do that. Can anybody tell me what happened in the video? What was it about? What happened? Did you watch it?
The video was about creating electricity moving a magnet in and out of a coil or loop.
So, the video was about producing electricity by moving a magnet through a loop. Now think about that. Producing electricity by moving a magnet through a loop. Anybody ever seen one of those flashlights? The flashlight, you shake it up and down, and you can charge the light, and you can turn it on. Or have you ever seen the kind of radio that has a little crank on the side? You crank the radio, and you crank it for a while, and you can charge the radio up, and then you can play the radio. If you've seen those devices before, what you've seen is an application of what you saw in the video. The person in the video actually produced electricity using a magnet and a coil. Up until now, the only way we can get electricity is out of a battery. DC circuits was about batteries. We get electricity from batteries. A battery works on electrochemical action. It's chemistry. Now we can produce electricity. No chemistry involved. It's all physics. He took a magnet. And let's talk about exactly what he did. He took a coil with one loop, one turn, and he took a magnet, and he moved the magnet through the coil. And what you saw, there was a meter. And that meter was kind of interesting because a lot of times a needle will sit over here or over here on the meter on the device, but that needle was right in the middle. It was right in the middle. And what you saw was when he moved the magnet one way, the needle deflected one way. When he pulled it back, it went the other way. If he moved it back and forth like this, that needle will alternate back and forth. So one thing you should have observed is that the direction he moved the magnet through the coil dictated which way the needle would move. It would move one way. If he moved it one way, he pulled it back, it would go the other way. If he moved it in and out like this, that needle would just alternate back and forth. We did that with one loop, one turn of wire. And then he got 10 turns of wire and did the same experiment, and you saw the same thing. You saw the needle move one way and then the other way, but it moved further in both directions because the more coils he had, the more voltage was produced. And then to prove that, he went from one loop to 10 loops. When he got to 100 loops, you can really see the needle deflect as he moved it back and forth. It went back and forth. The back and forth, because the point of it is that when you produce electricity in that manner, you got to have something move. It moves one way, the needle moves one way, pull it back, it moves the other way. If you keep that motion going, that needle is going to alternate back and forth, indicating that the type of electricity you're producing when you do it in that manner is alternating current. And so what he really demonstrated, though, was something called Faraday's law. Now, again, if you had me for DC, we talked about Faraday's law in detail. We talked about it. But let's remind ourselves of what is Faraday's law. What is it about? Well, basically, a demonstration of Faraday's law was what you saw in the video, but I want to write down some words to represent what we saw. Michael Faraday said that we can produce an AC voltage, which if I put that voltage across a closed circuit, which produces an AC current, we can produce an AC voltage. We can generate or induce a voltage if I have three things. I gotta have a conductor, and usually the conductor is in the form of a coil. So I'll say a coil, but in parentheses I'll say conductor, because that's what it really is. So you gotta have a coil, you gotta have a magnetic field. What else do we gotta do? We gotta have a coil or conductor, we gotta have magnetism. What else do we need?
You gotta have a movement too.
You gotta have motion. I gotta have motion. So Faraday says we can produce electricity if I have a conductor, if I have a magnetic field, and if I have relative motion between the coil and the magnet. So in the video, the person held the coil stationary and moved the magnet. If he wanted to, he could hold the magnet stationary and move the coil. Faraday says, I don't care how you do it, it's just got to be relative motion between the magnet and the coil. You take away any one of these, and you can't produce electricity that way. So when you produce electricity using Faraday's law, when you produce it that way, the type of electricity you get is AC. And what the guy demonstrated in the video, it was a demonstration of Faraday's law. It's called generator action. That's what this is. Faraday's law, generator action. I don't need a battery to chemically produce a voltage. I can do it electromagnetically. I can generate it based on Faraday's law. I can generate it, generator action. If you had me for DC, when we talked about magnetism, you might remember we briefly talked about motor action. If you go back and look at your notes, we talked about motor action. This is the opposite of motor action. This is generator action. And if I have time, I might go and explore the difference between the two. So, any generator basically is based on these things. What the guy had in the video, that is a simple generator. That's a coil of wire and a magnet is the simplest generator you can have. That's an AC generator. And the more coils he put on his generator, the more voltage it produces. So all a generator is, all a generator is this: coil, magnet, and some way to move the magnet or the coil or both. That's all a generator is. So let's explore this. Let's dig into this a little bit. I want to make a generator. Let's make a generator. So here's what I can do. To make a generator, according to Faraday, all I got to do is I gotta have a magnet. So here's my magnet. I'm going to get two magnets. And if you remember your magnetism, magnets have a north pole and a south pole. So my magnets, these are magnets. Here's my north pole, here's my south pole, and I'm going to draw the magnetic field going from north to south. Now, I'm going to ask a question now. Now, again, if you had me for DC, you should know the answer to this. If you had somebody else, you might know the answer to it. I don't know how they taught it. But if you one of my students, I want to know what is voltage? What is voltage? Let me see what I have in my student. Michael, you should know. Daniel, Maybe some of the, Abdul, were you in my class? Is this the Abdul that was in my class?
Yeah, but
Okay.
it was a long time though.
Okay. Well, Abdul, you might have forgot since it was a long time ago. Can anybody define for me what is voltage? What is voltage?
The voltage is the difference potential.
Okay. You said a difference of potential?
Yes.
Okay. That's true. I'm looking for something specific that we talked about in DC. What do I need to do to create voltage? What do I need to do?
It's a difference in electric charge.
Okay. All right. I think that's Jacob again. So what we learned in DC was to make a voltage, what I do is I got to separate charge. A voltage is a separation of charge. I don't want to get into the physics again because it takes too much time and I get carried away with it. But basically, what a battery does is it separates plus and minus charge. It separates it. So if I want to make a voltage, all I got to do is figure out a way to separate charge. Batteries do it through chemistry, electrochemical action, and we can separate charge. But anytime you separate charge, you got a voltage. So what I want to do is produce a voltage across a wire. I want to take a wire and move it through here and produce a voltage on the wire. Now, how do I do that? Well, that's what this lecture is about. I want you to think about something. I'm going to kind of take I'm going to go around the block on this one, guys, but just think about this. Think about what will happen if I do this. Oh, before I get into this, I got to show you something. Anybody know what a vector is? What's a vector? What is that? Anybody ever heard of that? A vector.
A vector is a mathematical property of has a direction and a magnitude.
Okay. So a vector is a quantity that has direction and magnitude, size and direction, as opposed to things that don't have that, they just have size. So in physics or science, they talk about scalars and vectors, and again, you don't have to get into the details of this to know what I'm talking about. Just realize there's two kind of quantities in the universe: vectors and non-vectors. A non-vector is called a scalar. So some quantities don't depend on direction, like temperature. It's 32 degrees outside. We don't care what direction, it's 32 degrees outside. But some quantities depend on size and direction. Some examples of that would be force, acceleration, velocity. These are all vectors. Okay, so don't worry about that. What I want you to worry about, though, is the way I represent a vector. The way I represent a vector is an arrow. With the arrow, the length of the arrow represents the magnitude, and the way it's pointing represents the direction. So let's say that I got vector A like that, and I got vector B. But vector B is twice the length of vector A. What I got to do is I got to measure vector A and then draw vector B twice as long. So I can have a vector and represent it as an arrow. And the thing about a vector is I can take the vector and move it any way I want. I can move this vector anywhere in the whole universe, and it's still the same vector as long as I don't make it shorter or longer or tilt it. I don't change the direction. I can move it around anywhere in the whole universe. The vector, I can move it. So vectors are pretty easy to draw because all I got to do is draw the right length at the right angle. I mean, the right length at the correct angle. So I might draw a vector like this. I might draw a vector like that. I might draw it like this. So I can draw these vectors, these quantities represented as vectors, but I got a problem if I want to show a vector coming towards you, because I'm drawing the vector in the plane of the board. So what I want to do is be able to draw a vector towards you. So like, let's say this vector right here, here's the vector, here's your eyeball. You're looking, here's the vector, the arrow, and you're looking at that vector. There's your eyeball. if I take the vector and turn it towards you, then what you see by looking at the tip of that vector, you see this. You see this, and there's the point of the arrow right there. You see the point of the arrow, the point of the vector. So if I draw a circle with a dot, that represents a vector coming towards you. Well, what if you're looking at this side of the vector? Here the vector is going towards your eyeball. You see this? And here I'm indicating in the picture that it's going away from your eyeball. How do I draw that? And the way you draw it is you just draw a circle with an X on it. So this represents a vector coming toward you. If I turn it this way, this represents a vector going away from you. So if you follow that, now I can draw a vector anywhere in the plane of the board, and I can even draw one coming towards you if I draw it this way, and going away from you if I draw it that way. This is the dot X notation to draw vectors. So if you follow that, then I'll come back to that in a second. Now I want to do a little experiment here. Let's say I set this up. I got two magnets. I put the two magnets real close to each other like this. I got a north pole and a south pole. Now what I'm going to do is I'm going to get another magnet. Here's a little magnet over here. And what I want to get, I want this north pole right there. I want the north pole. So I'm going to get something to cut that metal, the magnet wood. A saw. I'm going to saw it in half. I'm going to saw it in half so I can get that north pole. So I got my north pole here. Will that really work, by the way? Can I take a magnet and saw it in half to get the north pole? Can I really do that?
I don't think it will work.
It won't work. That's silly. It won't work. What I'll get is two smaller magnets. And I can cut it again. I'll have four smaller magnets. But let's remember when you were a kid and you would play. Just play like you can really do that. Let's act like I can really take a magnet and cut it in half and get just the north pole and just the south pole. And not only that, let's go wild with our imagination. So I got this square magnet. I want to cut it so that the corners are round. Matter of fact, it's not even round, it's a sphere. I got these balls, these magnetic balls. I have 3 of them. I got 3 balls. One of these is a north pole. One of these is a south pole. And this one right here has no magnetic property whatsoever. None. And the reason I made these balls is because imagine, you know how they play, you guys ever seen a poker game? You probably don't watch poker. But when they play poker, you know, they got the people sitting around the table, and they always have a camera up above so you can look down and see the cards. You ever seen that before? Imagine looking down at this. You got a God's eye view. You're looking down at this, at a table, and they got these 3 balls, spheres. One is a magnetic south pole, one is a magnetic north pole, and the other has no magnetic polarity whatsoever. And what I'm going to do is I'm going to hit that ball, and it's going to roll over this way. And tell me what's going to happen when it gets in here. What's going to happen? This is a north pole, and it rolls into here. What's going to happen when it gets into that magnetic field?
It'll travel to the south.
It will try to stick to the south pole, the other magnet.
It's going to stick to the south pole. I think she said it's going to travel with it. We all know that if I take a south and a north, they stick together. If I take a north and a south, they stick together. Take a south and a south, they push apart. I take a north and a south, they push apart. So in other words, if I have magnetic polarities that are the same, 2 norths and 2 souths, they repel. But if I have a north and a south, they attract. So I think what was said was, if that ball rolls into here, as soon as it gets in there, that south pole is going to stick to the south. And this one right here, it's going to do the same thing. It's going to roll in here, and as soon as this gets in here, it's going to stick to the north. But what about this one that has no magnetic polarity at all? What will it do? Well, it's going to roll straight through. Nothing's going to happen. All right, well, let's do this a different way. Instead of just hitting this North Pole and slowly rolling this in there so it gets stuck to the South Pole, let's say I hit it really hard and it's moving super fast. It's moving super fast. Here's what's going to happen. It's going to move in a straight line. It's going to move in a straight line until it gets in the field here, the magnetic field. Now, the magnetic field is pushing down on it. So what's going to happen is it's going to move in a straight line, and as soon as it gets in the magnetic field between the two magnets, there's a downward force on it, so it's going to move down like this. But let's say it's moving so fast that it just goes right past the South Pole. It never gets a chance to get stuck to it. It hits something down here, a target down there. And this is going to do the same thing, right? It's going to roll through, and if I roll it fast enough, it's going to go straight. Well, it's going to feel a force towards the north, but it comes up like this. Once it's out of the magnetic field here, it's going to move in a straight line again. And this one, which has no magnetic polarity at all, it's going to roll through. It's not going to be affected at all because it's not affected by north or south poles. Now, here's the cool thing about what I just did. If I know which one of these is north and which one of these is south, you can tell what's going. You never have to see this right here. You can tell if it's hitting. If you know this is a north pole, if the thing is hitting your eye here, you know it had to be a south coming through. If it's hitting down here, you know it had to be a north coming through. If it's coming right here in the middle, you know it has to be something with no magnetic properties at all. Now you might say, well, why are we even talking about this stuff? This is kind of, I mean, why are we talking about this? Well, this is actually a way that scientists use to separate subatomic particles. What I'm saying is this. It's true that I cannot take a magnet. I cannot take a magnet with a north and a south pole and cut it in half and get a north pole. I can't do that. It's physically impossible to do that. However, it is possible to get a magnetic north polarity and the magnetic south polarity. And I'm not going to talk about why it's true. I'll tell you where you get them from, though. Charge. Anytime I take charge and I move it, then that charge has associated with it a magnetic field. Now, this is just basic physics I'm talking about. Anytime you take charge and you move it, then associated with charge and motion is a magnetic field. And depending on what type of charge you have, the magnetic field produced will either be of a north polarity or south pole polarity. It'll be one or the other. Now, you got to go back to, I don't know if you guys talked about this in your DC class, but we did. We talked about two types of charge, right? We know there's positive charge and there's negative charge. We know that the positive charge comes from, there's three subatomic particles. This right here is a proton. This right here is an electron. This right here is a neutron. So if you go back and you probably study your atoms, you know, you got the atom, you draw the nucleus, you draw the electron going around. The electron has a negative charge, and the proton and the neutrons are like in the nucleus. You did all that in some class before. What I'm trying to tell you tonight, though, guys, is this, that if you take a charged particle, a proton or an electron, and you move it, then it has magnetic properties while it's in motion. If you stop the motion, the magnetic properties goes away. As long as it's moving, though, there's magnetic field associated with it. And if the positive charge behaves like a north pole, then the negative charge will behave like a south pole. I don't know, I don't remember which it is, but whichever is true, whatever is true for the one, the opposite is true for the other. That's all you really got to know. So because this proton has charge, if I move it, while I'm moving it, it acts like a little tiny microscopic magnet that has a certain magnetic polarity like a north pole. And if I have an electron, since if I move it, as long as it's moving, it has magnetic field associated, well, that acts like, let's say, a south pole. And the neutron, which is neutral, has no charge at all. If I move it, nothing happens. There's no magnetic polarity associated with it because it doesn't have any charge. Neutrons don't have charge. So instead of having a magnet, I can have a positive charge here. I can have an electron here, and I can have a neutron here. Now, earlier when I said this is the way physicists separate subatomic particles, you might have heard of something called a super collider. They have these big rings and they accelerate particles around, they smash them into each other, and then they see what comes out. Well, they don't literally mean they see what comes out. They have a device like this that you can actually separate these subatomic particles basically by running them through a magnetic field exactly like this. Now, I don't want to get into the physics of this. What I really want to get to is this. Here's what I want to get to. It's pretty simple. Anytime a charged particle goes through a magnetic field, there's always a sideways force that acts on it. Now, this is the start of AC. Right now, we're talking about how to build a generator. Actually, we're not talking about that. We're talking about why generators work. So what I said was, anytime a charged particle moves through a magnetic field, it experiences a sideways force. Anytime a charged particle moves through a magnetic field, it experiences a sideways force. And I was trying to show you here that if my charged particle is a proton, it's going to move through here and keep straight, but then as soon as it gets in the magnetic field, it's going to experience a sideways force, which is why I have it going up this way. And the same with the electron. It's going to move in a straight trajectory, a straight line. And as soon as it gets in that magnetic field, it's going to experience a sideways force and move down that way. But the neutron, which has no magnetic properties whatsoever because it doesn't have any charge, it's going to go right through the magnetic field and go through and not be affected. I want to talk about, though, what I said was right. What I have that's wrong is the direction of the sideways force. The sideways force isn't really like this or like this. How or in what direction is the force really applied on the charge as you move it through a magnetic field? And to talk about that, I want to talk about something called the right-hand rule. Now, I hope you guys are following this because this works a lot better in person than through a camera. But I want to talk about the right-hand rule. Now, let me pause for a second. I'm only talking to now the people who understand vectors. If you study in either math or physics, vectors. I think I asked what a vector is. I think it was Jacob or somebody gave me the correct definition of a vector. So you may have taken a physics course or a math course or calculus and you talked about vectors. A vector is a quantity that has both magnitude and direction. We know that. Okay, so that's a vector. But see, you can do arithmetic with vectors. You can do vector, you can divide, multiply, whatever you can do with regular numbers, you can do that with vectors also. So vector multiplication is interesting because when you multiply two vectors, there's names to there's two ways you can multiply, or two results of multiplying vectors. Again, I'm only talking to right now the people that know vectors. If you don't know what a vector is, just ignore what I'm saying. Okay, but if you know what a vector is, you might remember when you study vectors, sometimes you take a vector times a vector. Sometimes you take a vector times a vector and you get another vector. And sometimes you take a vector times a vector and you get a scalar, something that's not a vector. Well, in your math or physics class, you call this case a cross product, and this was a dot product when they taught you that in physics. Okay, so if I take a vector times a vector and get a scalar, that's like taking like work is a perfect example, right? So if you have physics, force is a vector, displacement is a vector. You multiply them together, you get work, which is not a vector. So that's this one. A vector times a vector gives you something that's not a vector. But sometimes you take a vector times a vector and you get something that is a vector, and that's the cross product. And it's kind of confusing because the cross product works like this. Say I got the vector like this, and I got another vector like this, and I multiply them together. The vector I get is, if you think about this as a plane, it's sticking up like that. Now, what I'm saying is very confusing and complicated, especially if you don't know vectors, which is why I mentioned the right-hand rule. Because what we're really doing, guys, what I'm showing you here is this thing called a cross product. But most of you, or probably many of you, don't even know what I'm talking about. So that we don't have to do any of this, somebody made up something called the right-hand rule. And a baby can understand this. So instead of understanding all this complicated vector math, all that stuff, we can do the same thing if we understand the right-hand rule. So I want to explain the right-hand rule right now. The right-hand rule says this. You start with your right hand, right? So I'm looking at this magnet thing right here. So your right hand, you got three parts of your hand you're concerned about. Your thumb, your fingers, and the palm of your hand. Your thumb, fingers, and the palm of your hand. You got to use your right hand. And what you're going to do is, let's say I got a charged particle. Here's my charge. So I got a plus charge. Now, the question I'm trying to answer right now, so I want to be clear. The question I'm trying to answer is this. I know that if I move this charge through the magnetic field, it's going to experience a sideways force. The question I'm trying to answer is, what's the direction of that force? What's the direction? Well, I can use the right-hand rule to determine the direction of the force on this charge. That's going to tell me which way the charge will move. So if I use the right-hand rule, my thumb points in the direction that the charge is moving. The charge is moving this way. So my thumb points in the direction the charge is moving, and my fingers, see the fingers look like the magnetic field? My fingers point in the direction of the magnetic flux, the magnetic field. The palm of my hand shows the direction of the force on the charge. I'm going to say that a second time. I'm using the right-hand rule. The right-hand rule on this charge right here. My thumb points in the direction that the charge is moving. My fingers point in the direction that the magnetic field is moving. And the palm of my hand shows the direction of the force on the charge. Now remember what I said about the dot and the X? The dot represents a vector moving towards you, towards the camera, and the X represents a vector moving away from you, away from the camera. So the palm of my hand, I'm going to draw on my hand. So on my hand, I'm going to draw this. On the palm of my hand, I'm going to draw a circle with a dot. And on the back of my hand, I'm going to draw a circle with an X. Because the right-hand rule, my thumb goes in the direction of the charge, my fingers go in the direction of the magnetic flux, the magnetic field, and the palm of my hand is the direction of the force on the charge. So right now, there's a circle with a dot, so the force is towards the camera. So here's what happens. The charge moves this way, my thumb, the magnetic field is this way, the force on the charge is towards you. So this charge is going to come in and move around that way, as long as it's in the magnetic field. Okay, well, what happens if the charge starts over here and moves back the other way? So if the motion is this way, the force is towards you. But if it comes back the other way, now the palm of my hand is into the board. You're looking at the X. The motion is into the board. I don't know if you're following that because I can't see your faces. But hopefully with that right-hand rule, you can see that if I have an arrow coming out towards you, That's the direction of the force. If I reverse that, then the arrow is going into the board. Now here's a better picture, guys. Look at that packet I gave you. Look at your screen. I'm going to bring that packet back up. I actually have a diagram that shows the right hand rule. So let me bring it back up. All right, so take a look at this. Again, remember, you can always magnify the paper, make it bigger by clicking that little thing over on the side. You can make it bigger, okay? But what you see here, you see a charge right here. You see this charge. And the charge has that V right there, that stands for velocity. That's what the charge is moving. The charge is moving toward vector V. The B is in boy. The B is the direction of the magnetic field. And the F is the direction of the force on the charge. But they're showing you the right hand down here. You can use the right hand rule, and they're showing you exactly what I was trying to show you. What I said was that if you let your fingers point in the direction of the magnetic field and your thumb point in the direction of the charge, the palm of your hand points in the direction of the force on the charge. If I flip the hand over, you can see the arrow right here. If I flip it over, if I flip the hand over, the arrow will be down here like that. Hopefully that makes sense. Now, why am I showing you this? What's the point of all of this? Well, the point is this. It's pretty simple. The point is that if I take a piece of copper, a copper wire, copper bar, remember what we said about voltage. I asked earlier, what is voltage? And the answer is voltage is a separation of charge. Any way you can separate charge, if you separate charge, you create a voltage. Batteries separate charge. I want to show you there's another way to separate charge by simply taking a copper wire and moving it through a magnetic field. If I move the wire through a magnetic field, as long as the wire is in the magnetic field, there's a sideways force that acts on it based on that right-hand rule I just described. It's going to push all the electrons down, not all electrons. It's going to push many of the electrons down to one end of the wire as long as it's moving through the magnetic field. Now, the wire in the beginning was neutral. The electrons were only pushed to one end when they got into the magnetic field between the two magnets, which means that if this end is negative, it has an excess of charge, then this is missing charge, this end is going to be positive. So as long as I have a situation like this, there is a voltage, a potential difference between that point and that point. I can create voltage using the battery, or as long as I have that wire moving in that magnetic field, while it's in the magnetic field, I got this situation. I got a voltage produced because through electromechanical action, I can separate the charge. But here's what happens. If I move the conductor through this way, notice, let me get my prop here. Notice my palm of my hand is the direction that the charge is being pushed. So if I move the wire this way, I don't know if you can see that on my hand. There's a circle and there's a dot. Circle with a dot and the cross. So if I move the wire this way, then the force is towards you. If I bring the wire back this way, the force is into the board. So if I take this, say this is a piece of copper, and I just do like this. When I move it one way, the polarity is like this. But when I bring it back, the polarity is like this. Positive, negative, positive, negative. The direction of the conductor through the magnetic field determines the polarity of the voltage produced across the wire that I'm moving back and forth. So what's going to happen is if I move it one way, I get one polarity. If I move it the other way, the polarity reverses. If I just do like this, the polarity is going to alternate between plus and minus, and plus and minus. It's going to alternate back and forth. And basically what I've done is created a simple generator. you can actually, if there was a way to do this, you can actually take this metal wire. If there was a way to hook a light bulb to it and hook it up, if you did this fast enough, you can actually get that light bulb to light up. Now, you'll never do it fast enough because you can't move that fast. But in theory, you could. You can take a piece of wire, hook a light bulb to it, and do like this. As long as you run that magnet of the wire through a magnetic field, it creates electricity, and that light bulb will blink off and on. It'll blink off, it'll blink on, and then when you pull it back, it'll blink off and on. And what's happening is the current is going one direction through the light bulb. When you pull it back, it's going the other direction. You have made a simple generator by just doing this. The problem is it's not a very efficient generator. You're going to get tired doing this. So that's not a very good way to design a generator. So here's what we do. Instead of having a straight piece of wire like this, that I got to move back and forth like this, what happens if I make a coil? Let's make a coil. Let's take this copper. I'm going to erase this and draw it a little bit neater. Got the same setup. North and South Pole. But now, instead of having a straight piece of copper, I'm going to take the wire and bend it into a coil like this. And you may wonder, well, why do I do that? Well, remember, Faraday says that I got to have magnetic field, I got to have a conductor, and I got to have motion. So I was getting motion by doing this. That type of motion, that translational motion, is hard to get. If I take a coil, if I take the wire and I bend it like this, and stick that in there like this, now what I can do is I can hook a shaft to this, and once I hook the shaft to this, I can get this thing to spin. It's easy to do. I can put, maybe I put a wheel here and a belt, and I can have a motor spin this. Or maybe I put some, like a turbine there, and I can have wind blow across this and spin it. I can put this under a waterfall, and that waterfall on it and spin it. I can take water, heat it up, and let steam shoot up. Some kind of way I got to spin this thing, and there's a lot of ways to do it if my motion is rotational instead of translational like that. So when I make a generator, you never see a generator where there's a wire moving back and forth like that. It always spins because rotational motion is really easy to get. So I can actually take the wire, bend it into a shape of a coil, and when I do that, I can hook a light bulb to this. So I take a light bulb, hook it up, and now when I spin this, the guy in the video, he took the coil and he did back and forth like this. You saw the meter move. You can take the meter off, hook up a really low power light bulb, and the light bulb could blink off and on. Same thing, produce electricity. Instead of doing this, you could have spun this wire in a magnetic field. You could have spun it if I had a coil instead of a straight wire and get the light bulb to light up or the meter to move, either way. The problem is, you might be looking and saying, well, that won't work because my wires are going to twist up. I got a couple times to get this thing to spin, the wires will spin and break off. So my generator isn't going to work too well if the wires break off. So what do I do? Well, imagine I have a copper pipe, a small copper pipe. Let me draw it. Got a copper pipe. Here's my pipe. And I'm going to just cut a little piece off of that copper pipe. So cut that piece off. I'm going to set that piece up. If I set it up so you can see it, it looks like that. So the copper pipe, I cut it off and I got this ring. right? I got the ring, and what I'm going to do is cut the ring in half like this. So now I got 2 half circles made out of copper. What they do is they take the top part of this ring, go back to my coil over here. They take the top part of this ring and they put right here on the top wire, the bottom part of that ring, and they put on the bottom right here. Now, I'm not drawing it very well, but if I draw the conductor like this, that top ring, if you're looking at that wire, that wire right there is like right here, and this wire is like right here. So your eyeball is looking at the edge of that wire, it's right here. And if your eyeball is looking at the edge of that wire, it's right here. So we weld these rings onto that coil. And if I do that, now what I can do is I can get 2 pieces of metal, one like this and one like this. And maybe I got a spring that pushes down on this, and pushes up on that to keep these metal, they're called brushes, against these rings. And now I can take my light bulb and hook up, and this thing can spin inside of here and maintain contact, and the wires won't twist. Well, I'm trying to describe something. I actually have a picture of it. Let me show it to you. Go back to that document I just showed you. Go back to that. And here's what I'm trying to describe to you. This right here. You see, I have a coil. You see, I have a north pole and a south pole from 2 magnets. And you see the magnetic field always goes from north to south. And I have this coil that I can rotate. Show the direction of rotation. I can rotate that by putting a shaft over here on the end. And again, I can put a wheel on here and over a pulley like in your car. There's a generator in your car that has a pulley on it that goes across your engine, and your engine turns the generator. Or I can put a windmill on here, a turbine, so the wind can spin it, or water, some kind of way I got to spin this. But over here is what I was trying to draw. This right here, this part right here, and this part right here. These are those metal rings I was trying to draw. And this allows us, here it's drawn a little differently than what I had, but you can get the idea. There's a way that I can take this coil and just have these brushes right against these rings, and now I can turn this thing through 360 degrees, and the wires won't twist and they won't get twisted and break off, because these brushes allow free motion through 360 degrees, and I can go around and around and around, and the wires never twist. So I get electricity flowing through the load. They're showing a resistor, but it could be a light bulb or the meter that was in the video you watched. Basically, I'm producing electricity, not using the battery, but this time using electromagnetic, basically Faraday's law, electromagnetic forces. Okay? So, what I've shown you here is a generator. This is a basic generator. Okay, so that was a lot, guys. So hopefully you at least kind of followed that and got something out of it. Now, I do want to talk about one more thing. I don't know if I want to actually get into the math until next week. I was going to do some calculation, but I feel myself not being able to do that right now. I mentioned earlier that we know that AC stands for alternating current. We know that. We've established that already. It turns out there's actually 3 different types of alternating current. Let me draw the waveforms on the board for you. I'll come back to this. So if you're taking notes, 3 types of AC. I'm just going to draw what they look like. One looks like this. And it keeps going. One looks like this. And it keeps going. And the other one looks like this. And it keeps going. Now, I hope you can see all three of these in the camera. If you can't, I'll describe these to you. This first one right here is called a sine wave. This is a sine wave. And it's alternating. Anytime you have part of the wave above, we'll call it the x-axis for now, but it's not really the x-axis. Anytime you have part of the wave above the axis and part below, then it's an alternating waveform. So here's an alternating waveform that's a sine wave, but the one below it is a triangle wave. And the one below that is a square wave. And it turns out that all three of these waveforms are different types of AC. So when I say AC, I really got to specify, are you talking about this type of AC, this type of AC, this type of AC? Are you talking about a sine wave, a triangle wave, or a square wave? Which one are you talking about? Well, it turns out that when we talk about AC, most of the time we're referring to this very top one right here. Not this one or this one. In this class, if I say AC, I mean that one. If I mean this one or that one, if I mean a triangle wave or square wave, I have to specifically name it. I have to say a triangle wave or square wave. I got to say it. If I just say AC, then we just mean this one. Now, what's special about this first one goes back to, there was a young lady I asked a question. I don't know the name, you guys' names yet, but I asked about, we go back to the diagram of ways to create AC. And I asked what was common about the first three ways to create AC. There was a generator, a big industrial generator. There was a small generator you hooked to an RV. And then there was like a windmill. And I said, all right, what's the same about all these? And somebody said they all involve rotation. We call that a rotating machine. And now you see why it's a rotating machine. This is what's inside of it. Any generator is going to have a set of fixed magnets, a coil that rotates. If you rotate it, you produce electricity in the form of AC. But not just any old AC, this kind of AC. All rotating machines produce sine waves of AC. Not a triangle wave, not a square wave. These are produced electronically. If I have a rotating machine, it's going to produce this one. Now I got a picture of that. Go back to that diagram that I showed you one more time. Let's visit that. And let's see if we can understand what's going on. So I'm going to try to explain this, and all I can say, guys, is just try to follow me. If you get a little confused, it's okay. I'm doing this more just kind of if you're curious what we're dealing with when we talk about generators, but everything that comes after this, you'll be able to. If you don't understand this 100%, you can still do very well in the course of this, attempting to try to explain some things that really probably would take me 2 weeks to do a good job to explain. But just kind of bear with me. So here's what we have. We basically have this generator, this one. And what they're showing you in this other picture is, imagine your eyeball is over here. You're looking over here. Here's your eyeball. I don't know if I can draw an eyeball. So here's your eyeball. And you're looking at this wire and this wire. So they kind of cut this wire right here. They kind of cut that out. It's really there. But you're just looking at this wire and this wire as this generator spins around. So if you follow that, that's what this picture is. That's what this is. So that part, this part right here, this part right here, that's the part you don't see in this other picture. It's there. It's like right across here, but they're not showing it. But what you have is you got two conductors. You got conductor A and conductor B. And what they want you to see here is two things that's important about this diagram. First of all, we start at this position 1. I'm going to call that 0 degrees. And what's going to happen is that coil is going to rotate this way. It's going to rotate counterclockwise. So the rotation of the coil is this way, around like this. Right? As this rotates, one conductor is going up and one conductor is going down. So the fact that they're moving in two different directions means that, let me go back to the camera. I want to go back to the camera. So let me see if I can show you this, because it's actually kind of neat. So what I'm trying to show you in that picture is the coil. So we got the coil. We got the coil. Now, this part right here, they're not showing in the diagram. It's there. They just kind of got it dotted in like this, because they want you to focus on this conductor, this one, and this conductor, that one. So they're not showing that. They're just showing these two wires. And then they take the two wires and they spin it like this. So it starts off in position 1. And what they're showing you is if I rotate it counterclockwise, one conductor is going up and one's going down. Well, you know from the right-hand rule, if something's going in one direction, the force is produced in one direction. Go back the other way, the force is in the opposite direction, which means electrons are pushed to one end if I go in one direction, and pushed to the other way if I go in the other direction, which means that if this wire right here is traveling, say it travels to get a polarity like this, the polarity across this one is going to be like that. It's going to be opposite because it travels in different directions. That's what they want you to see. If I have two conductors, I'll see if I can do it over here. If conductor A is going up and conductor B is going down, then because of the right-hand rule, one will have a polarity like this, the other have a polarity that's opposite. Actually, I don't have that drawn right. One have a polarity like this, and the other polarity would be opposite, like that. That's what they're trying to show you. Now, hopefully that makes sense. But the cool part of this is, if I unbend this, you can see what I really have is this. If I have two batteries, like I take a battery and another battery, plus, minus, if this is 2 volts and that's 2 volts, and across these two batteries I get 4 volts. If I have a plus polarity and a minus polarity, and a plus polarity and a minus polarity, then I add these up to get my 4. That's exactly what I have here. If I straighten that wire out, if you look at this, and this positive and that negative, if I straighten this out, I got the positive, got the negative polarity for that one, and I got that positive and that negative for that one. If this was a battery and that was a battery, let's say that was 2 volts and that was 2 volts, I get 4 across the whole thing. Across the way this works is that conductor spins around, I get voltages that add up, and that's called series 80. And again, if you had me for DC, we talked about series 80 sources. But the point is, let me get back, because I don't want this to get too confusing. The point is that as this rotates, and I follow the rotation around, then for the first half of the rotation, there's a couple things going on. As I mentioned before, I'm in position 1 here. Position 1, I don't know if you can see this or not, but this is conductor A and this is B. This little tiny A, let me see if I can It's a little tiny A right here and a little tiny B over here. One conductor's going up and the other's coming down. And as it moves from position 1 to position 2 to position 3, those conductors are cutting through more and more magnetic field. As a matter of fact, in position 1, it's not really cutting through much magnetic field. They're trying to show you that. They're trying to exaggerate the picture here. Position 2 is cutting through more flux. The maximum flux is cut through at 90 degrees. And down below, if you look at these two pictures very carefully, you'll see, compare figure A and figure 13.4 to figure A and figure 13.5. And what you'll see here, if you look carefully at this, is in this top figure, conductor A is moving up and conductor B is moving down. They go through these other positions, and down here, conductor A is moving down and conductor B is moving up. In other words, it went through a whole half cycle. It went through a whole half cycle. So to sum this up, here's what's happening. I don't know if you can see this or not, but you might want to magnify it. They're trying to show you what happens to the forces. The forces actually translate to voltage. So whatever's true for the force created on those charges that move in the coil, because of the right-hand rule, whatever's true for those forces is true for voltage. The more force, the more voltage. And so what happens is that coil goes around, starting at position 1, which is, we'll call it 0 degrees. You can see what happens to the voltage. This thing actually traces out a sine wave. And so I think the best thing to do is to try to compare this diagram. They're showing you this arrow right here. They're showing you the position of the coil. So this represents position 1, that's position 2. As it goes around at 90 degrees, you're cutting the most amount of flux, so you're producing the most amount of voltage. Down here, let's go to figure A. Figure A, we go back over here. In figure A, basically the conductor's in this position, right? So you're not cutting through much flux. In the next figure, you're cutting through more flux. At 90 degrees, you're cutting through the maximum amount of flux, or magnetism, magnetic field. Well, the more magnetic field you cut through, the greater voltage is produced. And so in this picture, they're trying to show you that at that first position, you're not cutting through much flux, so you're not getting the voltage produced. But as your angle increases, as that coil cuts more and more flux, the more voltage is produced. You cut through the maximum amount of magnetic field at 90 degrees, so you can get the maximum voltage produced at 90 degrees. Then once you go past 90 degrees, now you're cutting through less flux again, and so your voltage is going to drop off until you go through that first half circle. Now you're back to 0 again. So this diagram right here, represents the case where over here you went around the rotation, 1/2 rotation, and now these conductors A and B have changed places. So that's what that represents. So if you keep doing that, if you just keep going in a complete circle, the voltage waveform traced out, if you can see it, looks like what they're showing you right here, which is a sine wave. So I said a whole lot. It might be kind of confusing through the camera. What you want to focus on is this right here. If you go around with that generator coil one time, it's going to produce two maximum values. And I'm going to blow this up. I don't know if you guys, you might want to blow yours up. It's going to peak at 90 degrees. It's going to peak at 270 degrees. And you'll get 0 volts at 0 degrees, 180 degrees, and 360 degrees. If you keep on turning the generator, what's going to happen is that this waveform is just going to keep on reproducing itself. One time around the circle, one time around for the generator coil produces one of these. This is called a waveform. And every time you go around, it's going to produce another sine wave. If you continue to let your generator run, then you'll have a waveform produced that looks like what I'm drawing. So that's a lot, and I feel like, I don't know if I did a good job or not explaining that through the camera. It's a little easier to do face-to-face when we're not face-to-face. But here's the takeaway, guys, and I think I'm going to end this after that because we've been talking for a long time. Any type of rotating machine is going to produce AC, and if it's a rotating machine, the type of AC it's going to produce is not going to be a square wave, it's not going to be a triangle wave. All rotating machines produce sine waves. So the voltage sine wave and the current sine wave is what you get when you get AC produced by a generator. So what I want to do, not tonight, but I think we'll call the night now. And if you notice in this last diagram, there's something called period. We need to talk about the period and the frequency of this voltage waveform that's produced in the rotating machine. So we need to define the term period and frequency. And once I do that, you can do an analysis. You can do some calculations with this stuff we've been talking about. So we don't know enough yet to complete homework number 1. I think I have homework number 1 set to be due on the 28th, but you won't be able to turn it in on the 28th because I need to talk some more about some other things in order to do the homework. So I'm going to extend the due date on that first homework, and it won't be due next week. It'll probably be due the week after because I have to lecture some more. We have to talk about frequency, period, and a couple of other quantities to be able to do that homework. So I'll extend that homework, and we'll pick this lecture up and finish it next week. So I think I'm done for tonight. Does anybody have any questions or comments for me?
I actually have a quick question.
Sure.
If when you're discussing the generator here, if you had another pair of conductors on that spinning part there, would that create like twice as much electricity?
Okay, that's another good question. So wait a minute. Am I back on camera? Is the camera here?
Yeah.
Okay, so that's a good question. So that actually gets into, remember when I was going over the syllabus and I said, all right, the last topic is called polyphase systems. And I said we may or may not get to that. Well, the term poly means many. So here's what happens. If I have one coil, the voltage looks like this. For every coil, it produces a sine wave. So if I have one coil, I get a sine wave of voltage or current that looks like that. Well, I don't know if we'll get to polyphase systems or not, but with a polyphase system, what we do is we wind the coil so that I have many coils on one thing that rotates, right? One rigid body that rotates. So at that point, each coil is called a phase. So if I have one coil, it's a single phase. You can exchange the word phase and coil. Every coil produces a sine wave, so every phase will produce a sine wave. So I can have one coil to be single phase. I can have two coils to be double phase. I can have 3 coils. Well, when you get to more than 2, they just call it polyphase. Polyphase. So polyphase means I have a bunch of different coils, which is going to produce a lot of sine waves. So the question you asked was, though, does it produce, I think you asked, does it produce more voltage? Here's what happens. If I have, now typically, when we deal with more than one coil, we typically deal with 3 coils. So you can have as many as you want, but 2's not enough to do much. And when you get above 3, the machine becomes more complicated. So it's like this trade-off. We settle on 3 phases, 3 coils. We call that 3-phase. So what I have is, instead of having one coil, I have 3 coils. Let me draw this. I have 3 coils wound in a way to where they're 120 degrees apart. So I have one coil like this, one coil like this, and one coil like that. So let's say this is coil A, this is coil B, this is coil C. So I have all these coils together, and what happens is, since they're 120 degrees apart, that's 120 degrees, that's 120 degrees. What happens is I get 3 sine waves. I get 1 sine wave from this one. I need another color. I get another sine wave from this one, and I gotta draw it the right way. So it's like this. It's 120 degrees. I get 3 sine waves that are 120 degrees apart. So the question, I think that was Jacob, I'm not sure. The question you asked me was, do I get more, I think you said, do I get more electricity or voltage? You do get more voltage, not necessarily magnitude-wise. The peak value is the same, but what you get is a much more efficient signal, AC signal. And so when we transmit power, what I showed you kind of wasn't true, that diagram. In the diagram, it looked like single phase power, but we really, when we transfer power, we do it, that's Jacob, we do it the way that you're describing here. We have more than one coil. In the United States, we have 3 coils that generate 3 sine waves. So the signal is more complicated than what I'm showing you. But by transmitting 3 sine waves instead of 1 together, you get a much more efficient transmission of power. Let's call it a 3-phase system. So I'm not going to say you get more voltage, you get a higher efficiency. I think it's the correct way to think about it. You asked some good questions. I love it. Anybody else have a question? That was a really good question. So guys, let me say this. It's kind of like when you know you did a good job. I can't see your faces. This stuff is kind of abstract. I'm drawing things on the board. I'm trying to show you pictures because it's kind of hard to visualize this stuff. So I don't know how well I described what was going on. I'm going to come back to this next time. I'll probably briefly review this, but I want to really get to the math behind this because that's when we can start doing calculations. And hopefully from those calculations, we can gain some understanding. So I want to say this. I'm going to put the video up. You can go back and rewatch this. And part 2 of this will come next week. You can watch it till you kind of get it. You don't have to understand everything I talked about. You don't have to understand every detail. This is just trying to get you to kind of see what's under the hood and kind of see what's going on. And I think when we settle in and get past this stuff, we'll be more focused, and then I think the understanding will come then. So I guess what I'm saying is, don't feel frustrated. If you don't follow everything I said, you're still okay. Don't run out and drop the class or anything like that. Just kind of stick with me, and I think next week I'll focus in on some concepts. We'll talk about frequency, period, angular velocity, those kind of things. And when you see that stuff come together and do calculations with it, the practice problems on the sheet, you'll kind of see how this stuff fits together, and you'll be okay. Anybody have any questions or comments before I sign off? Any questions? Is it Mandy?
Yes, so what is the homework due next week? Will it be the lab or just?
Okay, good question. Okay, so if you look on Blackboard, the first homework, it may say to be announced. I don't know if I put a due date on it or not. I probably left the due date off because usually I don't get through this stuff on the first day. In a perfect world, I get through everything in lecture 1, but I never do that. So homework 1 will not be due next week. Homework 1, I'll give you at least 2 weeks on it because you don't know enough to do homework 1 yet. So homework 1 is not due next week. The lab, there's a lab. In theory, the lab is due next week, but we probably won't meet next week. Now, act like it's due because there's a lot of work you got to do for that lab. You're going to download it and read it. There's a lot of calculations, but the math in that lab you got to know to be able to do problems in this class. So I'll give that lab. If you do it, do a good job on it, it'll make what's coming later a lot easier. So in theory, the lab is due next week, but I'm not gonna collect it next week because you won't be here. So that's not due. You'll have 2 weeks for that. Now, what I can collect is there's a Tesla assignment. That's where you go and you watch the video on Nikola Tesla, and you write out a paper, and you'll submit that through Blackboard. That will be due next week. Okay, so the only thing you have to turn in is that Tesla video paper. You'll submit that through Blackboard. The homework and the lab, they won't be due next week, but you definitely want to start the lab and don't wait till the last minute to do it. It's going to take you a while to work through that lab. Okay, does that answer your question, Mandy?
Yes, thank you.
All right. Anybody else have a question? Okay, guys, have a great rest of the day. Please stay safe, and I will see you guys next week. And just watch Blackboard in case anything changes with the class or if I post something else. If you need me, send me a text, and have a great rest of the day.
You too. Thanks.